We're going now to continue the presentation. So now so far we're focusing on elastic response of the mortar. Now we're going to focus on the plastic response. So basically, now we have a point in the mortar that is experiencing a stress that is this much and higher. So when we shear stress that is this much or higher. So when we increase the load sigma zero applied onto the structure, more and more of the tablet will of the mortar will experience plastic deformation. So for us to understand what is going on here, we have to look at the regions between the brick and the mortar. So this is a drawing that I put for you of the bricks, this one, and the mortar that is in between them. So now, initially, when I reach the critical value of the load, this portion and this portion of the mortar will start deforming plastically. When I increase the loading, when I increase sigma zero, this plastic region will initially grow here and here in these regions. It starts to grow from the two ends. At some point, the interface in these regions will experience a shear strain that is equal to or larger than the gamma f, which means at this point that I'm showing with X on the two ends, the mortar, has failed. In these regions next to it, it has deformed plastically, and in the region in the middle, the behavior is still elastic. So sorry. I am just so now. So if I plot the shear stress in the tablet, which I'm showing you in this graph here, the shear stress in the tablet inside the regions that is failed is zero. There's basically tablet has failed there, and it's symmetric. So these two ends. In these regions where the tablet is deforming plastically, it's exactly equal to tau f, because if you remember, the stress strain curve response of the tablet is something like that. So every time that it's plastic, the shear stress is equal to tau f. Okay? And the region in between, we're experiencing an elastic response of the mortar. That's a qualitative understanding. Let's see what we can do to have a quantitative understanding of the mortar. Now, the material behavior changes when we're in the plastic regime. We have to use elastic perfectly plastic response. However, the equilibrium equations won't change. Still, equilibrium equations, exactly the way we drive them a few lectures ago, is still there. So, and that gives us some good understanding, because, for instance, in the regions that the interface has failed, tau is zero. If tau is zero, if I put tau equal to zero here, that means these two are zero, which means sigma 1 and sigma 2 are constants in the failed regions. in the regions that we have, the mortar has deformed plastically, the magnitude of the tau is equal to tau f. Again, put this value back into these equations, we get this. So in the failed regions, sigma 1 and sigma 2 are constants. Stresses in each tablet is constant. In the region in which the mortar is plastically deformed, sigma 1 and sigma 2 vary linearly because tau f over b is constant. So now, so we're on page 11 of the handout. Now, so again, let's look back at what we said before. This is going to be a quantitative understanding, qualitative quantitative understanding. In the regions that the mortar has failed, means in these two regions, sigma 1 and sigma 2 are constant. So at this far end in tablet 1, sigma is equal to sigma 0. And it has to be constant from equilibrium. We just derived it. So then it means all of it is sigma 0. At the far left end in tablet 1, this is only for tablet 1. At the far left end, tablet 1 is 0. And in the failed region, it has to remain constant. So all of this region is constant. We still don't know the length of the failed region, but whatever the length, it's sigma is given. And in addition to that, just considering symmetry, we can make the same arguments about sigma 2. Here it's 0, here is equal to sigma 0. Now, in this from here to here, or here to here, or here to here, or here to here, this is the region where the mortar has failed, has deformed plastically, which means d sigma dx is, d sigma 1 dx is tau f, d sigma 2 df is minus tau f divided by b. So basically, the slope of this line is b, the slope of tau f divided by b, the slope of this line is tau f divided by b, the slope of this line is minus tau f divided by b. So basically, these two regions, it's constant. These two regions are line and symmetry. So basically, these two regions are line and these two regions are constant. Okay, and the region in between is elastic. I'm going to highlight a few things in this slide, which I'm going to come back to later. One is that I'm calling the length of L1, and the length of the elastic region L1, the length of the plastic region in each side L2, and obviously we have these regions here and here that the length of them will be the combined length of this and that will be capital L minus 2L2 minus L1. Okay. We still don't know what L1 is. We still don't know what L2 is. We still don't know what how they're related to the applied load. But we're determined to figure those out. So, in order to understand that, to solve this problem, what I am going to do is I'm going to define another coordinate system which starts from here, and so basically x is measured from this end, and x prime is measured from this point, and this point is the border between failed and plastically deformed region on one end. And I measure the distance from here by variable x prime. I also noted that I have this points here. I show them with A, B, C, D, and E. Okay. So we're gonna stop here and we're gonna start with the next slide.